So I have two variables, x1 and x2. And for purposes of this exercise, let me suppose that I actually have the joint PDFs for my two classes of events, signal and background. So in real problems, you wouldn't have the PDFs available, but in this problem I do. And they're given in the box down here. And the way to think about the box is the following, is that the conditional PDF for x1 given x2, that's just a Gaussian, right? And for the two hypotheses, S and B, I'll have different mean values for the Gaussian, right? Now, the marginal PDF for x2 is just going to be an exponential, and that will be exactly the same for both S and B. And so I've given you now the conditional PDF for x1 given x2 and the marginal PDF for x2, and that of course tells you that the joint PDF for x2 is just equal to their product. And so here therefore are the two formulas. All right, so the joint PDF for x1 and x2 is just, first of all, a Gaussian centered about a mean that I'll call mu sub s, right? And it's got a standard deviation sigma, which is a given function of x2. And I'll take that function to be a constant that I call sigma 0 times an exponential term. All right, so that's just a formula that tells you what the sigma of the Gaussian is. All right, so that's the sigma of the Gaussian of x1 given x2. Right? And then here, the second term multiplies the marginal PDF of x2. So those formulas in the box basically define the model. Very simple model. And let me show you then on the next slide what the distributions look like. So here is a scatter plot of x1 versus x2. And so you can see that if you were to look at the fixed value of x2, then what you have is a Gaussian distribution in x1. Right? But the thing is that the sigma of the Gaussian depends on x2. It gets narrower when x2 gets large. So if I go back, you can see here the formula for the standard deviation, as it depends on x2, it gets smaller as x2 gets large. So it's as if that sigma represents maybe a measurement error or a measurement resolution. And you can see that you get good resolution when x2 comes out high, and you get bad resolution when x2 comes out low. Resolution for your measurement of x1. So anyway, that's what the scatter plot looks like. And if you project those down onto the x1 axis, for any fixed x2, the distribution of x1 is a Gaussian. But if I sum over a lot of Gaussians, all with different sigmas, the result is no longer a Gaussian. You can see that it's got a much sharper tip and it's got tails that fall off more slowly. All right, so those are the marginal PDFs of x1 for the two hypotheses. But here's what's interesting, is that if you project the dots onto the x2 axis for the two hypotheses, you get exponential distributions, and that is identically the same for the two distributions. All right? And so now that's the setup. Now here's the question. I want to distinguish between the two types of events, and I want to search for variables that will help me do that. And so I might immediately hit upon this variable x1. I look at the distribution of x1 and think, yeah, that works. You know, if I could somehow measure x1, then that would help me distinguish between the signal and the background. But then you look at x2, and you look at x2 and you might ask the same question. Does x2 help at all? If I were to construct a feature vector, would I include this information from x2? It has absolutely no discriminating power between the two hypotheses. So think about that for just a second. Let me open the chat window to see if somebody's telling me, yes, use x2, or no, x2 is useless. It turns out that x2 is useful. All right? And so here's why. Let me go back. Come on. First of all, remember that the optimal test statistic is just given by the likelihood ratio. And for many problems, we don't have the joint densities. But for this one, because it's just an example problem, we do. So I could write down, I had the formulas there for these joint densities. And if you just take their ratio and then take its log, you see that this is the value that you get, right? And you can see immediately here that x2 enters, right? So it turns out that x2 has some influence on this optimal test statistic. So for example, if you set that equal to a constant, then in the, oh God, writing on this thing is terrible. I better just not even try this. Constant. If you set that thing equal to a constant, then in the x1, x2 plane, curves of constant log t will depend on x2. So let's look at that. There it is. So there's the x1 versus x2 plane. And these curves here correspond to curves of constant t. So they could be boundaries of a critical region, each one corresponding to a test of a different size. So it looks like by knowing x2, you definitely can incorporate that into constructing the optimal test. Now, what I've done in the following boxes is that I've worked out the lines of the constant decision function for different types of classifiers that we have discussed. And so here is the Fisher discriminant. And what's kind of interesting for the Fisher discriminant is that here, line of constant test statistic, constant decision function are vertical, right? So here it's basically saying that all of the discrimination comes from the variable x1 and none of it from x2. But this is not the optimal one. This is the optimal one. The exact likelihood ratio, that's going to be the best. And so the question is then, how about some of the others? So let's look at the neural network. Here's a neural network with only one hidden layer with two nodes. So it doesn't have that much additional flexibility. There's not that many additional parameters built into it. And you can see what happens is that the curves start to get bent around a little bit so that they start to approximate a little bit better the optimal solution from the likelihood ratio. And then up above, they start to get strongly influenced by the training data. If there happens to be an event over here, then that bends the curve over to the right and so forth. All right, so that's from a neural network. That was using a larger number of training events than is what's indicated here on the plot. The plot probably only has, I forget, a few hundred or 100 points for each. The training samples that I used for these classifiers were based on 100,000 events of each type. All right, so if you had a chance to watch the very last lecture, I apologize that only came last night, you learned about boosted decision trees. And remember that a boosted decision tree is basically a series of cuts. And so this is what it looks like in the x1, x2 plane. You can see it's just it's a rectangular series of cuts. And here actually you can imagine that the boosted decision tree starts to do quite a bit better than the neural network. So if I go back, you can see that those lines of constant BDT output are very close to the lines of constant likelihood ratio. All right, that was with 200 boosting iterations using the AdaBoost algorithm. All right, let's keep going. Here's something that is new, and so you don't need to know about this, but I'll just mention that one of the things that you can do is work out what's called the ROC curve. ROC is a jargon from signal processing, and it stands for receiver operating characteristic. So that is very far removed from the type of application we're thinking about. But this is the jargon that was invented by engineers doing signal processing. And what it means in this context is you look at the signal efficiency versus 1 minus the background efficiency. So remember, this means the, I can't even write on this, this is terrible. Let me go out of full screen mode. Discard. Well, I think we're out of time, but no, I better describe this. If you'll just bear with me, just briefly draw. Okay, so remember that the signal efficiency, that was the probability that we reject the background hypothesis, so therefore that X was in the critical region of the test, given that the event was of the type signal, and then of course the background efficiency it was the corresponding thing. It was the probability, so background efficiency, not 1 minus the background efficiency, was the probability that the data vector x was in the critical region of the test, given the event is of the background type. Given the event is of the background type. And remember that the hypothesis that we're testing is that the event is of the background type. And so what you can do is you can then work out these efficiencies, these type 1 and type 2 error rates effectively. And so what you can see is that they, depending on the constant that you would set the test statistic equal to, that determines the size of the test. And so that determines the background efficiency. And so depending on which of the curves that you would use to define your test, you would have a point on, a different point on these curves. Now what you want to have is you want to have the size of the test be as small as possible. So you want to have 1 minus epsilon b to be as high as possible. And you want the power of the test, which is the signal efficiency, also to be as high as possible. So the best curve for a test is going to be as far to the upper right as possible. And you can see indeed that bounding curve on the upper right is the likelihood ratio. Everything else is inside that, to the lower left of it. You can see that there's one size of the test here where they all coincide. That corresponds to where you choose the boundary of the critical region to go right down the middle, because they all include that. They all include sort of the vertical line that goes right down the middle, even the Fisher discriminant. That vertical line down the middle from the exact likelihood ratio could also be obtained by a test using the Fisher discriminant. So for a test of exactly that size, then the likelihood ratio and the Fisher discriminant would work just as well. All right. I think that's about all we have time for. It's already up to 12 o'clock, and so we should stop. But maybe let me just make a final comment, and that is that even though the distribution of that variable x2 was the same for signal and background events, x1 and x2 are not independent. All right? And so that is the ultimate reason why using x2 as an input variable helps. And you can kind of understand why, because this x2 regulates the sigma of the Gaussian. And so you can see that for high x2, it's telling you that your measurement of x1 was very accurate. For low x2, your measurement of x1 was not very accurate. So if you just focus on x1, you have well-measured events, and if you have poorly measured events. If you mix all those events together, which is to say if you weren't to use the information from x2, then the good, well-measured events and the poorly measured events would all be jumbled together, and the poorly measured events would pollute the gold-plated, the really good events. On the other hand, if you use x2, that means that you are able to exploit all of the information from the really well-measured events, and you don't allow the poorly measured events to pollute them, to influence them. So qualitatively, at least, that's the reason why x2 helps. Okay, I apologize that was all a bit rushed in the last example. Should have left a little bit more time. But please have a look at the slides, and if